there are certain reasons. One reason maybe because of previous module on the dynamics and control. It's more like touch and go, so you are not really go to that detail. And after one semester or one week or whatever, some of the things you may not really capture. And now, once we learn further, okay, on the digital part, okay, there are certain essential information you need, okay, by the dynamics control. From my point of view, this module, at least my part, is pretty simple if you understand well in your dynamics control. Because this one actually does not talk much except convert to analog. Of course, when you rely on your good understanding about the existing dynamics modeling, the analog control system, then you only have to do one thing, is to digitize. Okay, and if you look back for whatever we have discussed so far, we only discussed like 2 or 3 blocks, which is the analog to digital conversion, differential equation to difference equation conversion, and then the digital to analog conversion. We only need the conversion part. Okay? Of course, because of the conversion, we need to involve some mathematics. And actually, the mathematics part in the digital control is easier than the continuous control. Why? The reason very simple. Because in the continuous domain, you have continuous numbers. You got integration, you got differentiation. But in the digital domain, you look at the mathematics. Instead of differential equation, what we have difference equation. For your dynamics and control, if you really look at the detail, if your system is second order, you have 2 times differentiation, or 1 differentiation, 1 integration. If your system don't even work complicated, go to third order, first order, fifth order, it's almost impossible to solve. Because you have the third, fourth, or fifth differential equation to solve. No way to solve analytically, right? But for difference equation, for the digital control, you only have the time delay. No matter you have 2 times, 3 times, 4 times, 8 times, it's just first order difference equation. It's just you have a multiple time delay. That's all. And if you look at the mathematic transform, if you really study well in your dynamics control, you are able to handle the Laplace transform. Then for the digital domain, what we have? The Z transform. Frankly, which one is easier? Do you think the Laplace transform is easier or the Z is easier? I think the Z transform is easier because Z transform you always do summation. You only do the derivative, right? For the Laplace transform, if you really look at the detail, you can see integration. And if you want to do the inverse, your inverse Laplace transform, I think is a headache, right? So, frankly, this module, I think sometimes you need to clear your mental block. Don't think this one is very difficult. First of all, this module compared with your dynamics and control is easier because the digital domain usually is easier than your continuous domain. Difference equation is just summation, abstractions. It's anyway, it only first order is like your polynomial function. No differential equation, no integrations. If you look at the transformation, the Z transform is much easier than your Laplace. And for this module, it may also give you a good opportunity of doing some motivation for you to relearn a little bit in the dynamics control. We talk about the S plan, then we talk about the equivalent conversion to the Z plan, right? So from your partition, your A plus Bj to your polar form, your magnitude Z and your phase angle phi, right? So there's certain opportunity for you to learn and learn and relearn. So this is part of the SIP, right? Okay. So of course, I did not teach you in your dynamics and control, and I do hope through my module you can also learn better, okay, from your dynamics and control as well. And some of students worry about exam, because I mentioned exam usually is very simple. And if from the exam concern, if you look at all the past year papers, this week and next week are most important. Almost every year, one question comes from this week's topic, and usually one question will come from next week. Okay, so for this week and next week, we will go slowly, and we will show you how to solve the problems. As I said, is also very pretty simple. Okay, so what we are going to talk about today. Okay, so far what we have learned. We have learned digital control system, the difference between your digital and your analog is. Instead of continuous data, you need to do the analog digital converter, you need to do the sampling, right? So yesterday we have spent a lot of time, not yesterday, 2 days ago, right? Last Friday we have spent a lot of time to talk about the signal equivalence. So we understand in the digital control we are dealing with digital signals. So we need to convert the analog signal to digital signal. Then later after control, we are going to convert the digital signal back to analog signal. So last chapter we spent a lot of time to talk about so-called equivalence between analog and digital. After you have done sampling, after you have done coding, how much is the variance from your original analog signal? So last chapter basically we are talking about the equivalence at the signal level. And from this week onwards, this week including next week, we are going to talk about the system equivalence. And previously a lot of students asked, hey, we have an S function in the continuous domain. In dynamics control, we have learned a lot of things about S function. We present our plan. We present our dynamics modeling in S function. We design our controller. Eventually, we write our computer. We write our controller in S function. And now in the digital controller, you have we don't have S. We have Z. So is there something we can directly link between the S and Z? If you still remember about 1 month ago, I have highlighted. In the digital control, there is no single mapping from S to Z. You cannot just refer to the table. Because we have the Laplace table, we have the Z control table, right? You cannot just simply map the table. Because that table is for the signal only. But now today we are going to discuss whether there is a certain way can we find out the equivalence from the S function to the Z function. If the answer is yes, but the answer is also not unique yes. What I mean is, you can find certain equivalent of the S function as a Z function. But it depends which approach you choose. What method you adopt, then the answer will be different. There is no identical mapping from S to Z. Okay, why? Because very simple. When we learn the conversion from differential equation to difference equation, what we have learned? We have learned certain thing is called approximation. Alright? So when we learn approximation, we have learned units forward, units backward, and also trapezoidal. And actually, if you want, you can also define other things. So it depends how you approximate differentiation to difference. Then you have a different equations, if you still remember. Still remember your PME, still remember your low-pass filter. For all those S function, we come out certain difference equations, right? By different approach you adopt, you may have difference. You may have a different equation. Even though your PID is the same, even though your dynamics modeling is the same, even though your S function is the same, right? By adopting units forward or backward, your answers will be different. So the mapping is not different. And today, we are going to introduce, okay, how can we find out certain equivalent, or so-called discrete equivalent, okay, the discrete equivalent to your S function. And this is something we call the emulation. And emulation is basically, we understand, in the digital control, there is no continuous function. There is no differentiation, no integration, no S function. we only have difference equation. So we have learned about 1 month ago. Give you differential equation, give you integration, give you PID, give you a continuous modeling. You are able to convert your differential equation to difference equation, right? And that one is very helpful if you are doing engineering. If you design a good controller, you want to program it into a microcontroller to control your pen, or to do a certain programming into your industry PC to control your air flight, or to control a certain manufacturing plant or pharmaceutical process, and so forth. So that difference equation is very important for the real-time control for you to do programming. But for mathematically, for example, you want to also apply some digital control techniques. So you want to adopt certain mathematical, right? So in the continuous domain, we have two things. One is the differential equation. Differential equation represented as this. But now, what you have another two approach. One is the space, the other is Laplace transform. So after you get the Laplace transform, you get your transfer function, your S. So in the digital domain, we have the same thing. We have the difference equation. We have the difference equation for you to program, for you to come out the controller into the real time. And on the other way, we also want to have some mathematical tools for you to design, for you to do analysis, for you to come out certain good controllers. So what we have, the Z function. So if you talk about the mapping, differential equation is corresponding to difference equations. And your S function is corresponding to the Z function in the digital domain. So in this course, in my part, basically we only introduce how to convert or how to find certain equation between your S and Z, between your differentiation to your difference, between your M log eta to your digital data. So how can we find out certain discrete equivalent? Okay, from a test. There are certain approaches, and today we are going to introduce some fundamental approach which has been generated from your units forward, backward, and trapezoidal process. So previously, we have learned how to approximate differentiation by units forward, backward. We have introduced how to approximate integration by forward rectangular, backward rectangular, as well as trapezoidal. We have derived the approximation, we have tried certain good exercises. We also proved actually the units forward backward is equivalent to the rectangular forward backward. It's just one is talk about differentiation, the other talk about integration. We can consider integration as anti-differentiation, or the differentiation as the reverse of integration, right? So basically the thing. So today we are going to further extend this tree. Okay? So today we are going to further discuss three approximations. One is forward, one is backward, the other is trapezoidal. And we are going to figure out how can we find out equivalent Z function by the S function. The approach is not difficult. This is something we have derived through some of the exercise, if you still remember, right? It's exercise 4. So through exercise 4, we have done certain equations or substitution of differentiation. Because we can consider the S operator as well. In your continuous domain, what is your S? S is differentiation, right? So if you have a forward method, what do we mean? We mean dEt over dt is what? Differentiation, right? Differentiation, right? And if you have done the Laplace transform, what does it mean? your EP is equal to your ES. And if you want to do the differentiation of your ES, what you have done? You have an S operator, right? So it's multiplied with S. Right? And in the continuous domain to the digit domain, what we have done before, we have done how to approximate differentiation to difference equation, right? So if we are adopting the Euler's forward, so what are these differentiation can be? This one will be so this is something what we have done before. Yes or no? No. If no means you are absent, right? Either physically or mentally, right? But I hope at least at the moment everybody agree with this one. This one okay, right? So what does this one mean? We use the forward method to approximate the differentiation, right? So if you look in the time domain, you see your differentiation of your EP is equivalent or approximated to your next, your forward step minus your current step, divided by the time difference, right? And this is what we describe in the figure. So you look at the next step. And if you are talking about the integration, what the integration talking about? So this one will be your EK plus your EK plus 1 like right? So will be your current value multiplied with this rectangular, right? So this one is if your UV is equal to integration, then this one should be your UA. Your UA should be your UK minus 1 plus your EA.
我头名是哦，拉什么名字？
So this is your Euler's forward, this is your rectangular forward. This one is the same thing. If we do the mapping, what we get for this one? If we do the Z transform, if you do the differentiation, is you are doing the S operation, right? So your S operation, it means your S ES is equal to your ES multiplied with your S, right? So your S operator should be your differentiation divided by your original function, right? Then if you look at the Z transform, your plus 1 minus 1 in the time delay is what? Is multiplied with Z. Means multiplied with Z or minus 1, right? So your time delay will become a multiplication of Z. Then for this one, if your EK eventually is going to map with your Ez, right? Then your Ek plus 1 is going to map with your Ez multiplied with Z. Yes or no? Yes, huh? Then your S operator is going to map with your Ez multiplied with Z minus your Ez. Divide by this one to this one. This is something actually we have done during our exercise 4. Isn't it? So this is your Euler's forward. And if you have your Euler's backward, what do you have?
난 정신写的感觉呢。你注意看。
So this is your Euler's backward, right? If you are talking about the integration,
这是 backward， 又有 minus， 没有这个，我有这个 minus， 是 backward。assuming 啊，哦，这是 forward， 那它这边有什么什么呀？那你先抄。
So this will be your integration for the Euler's backward. Because we are referring to this point of UK, then backward is rectangular. So it's your EK multiplied with E prime. This is your EK multiplied with your E. And correspondingly, your S operator will be your Ez minus your Ez multiplied with
上个礼
your
拜
Z power
有剪了吗？
divided by T
有吗？
will be your
让他剪头发，他上个拜五跟他一样。
S equivalent to your
Ben，
Ez, right? So your S operator will be 1 minus Z power 1 divided by T. Or if you want, you can multiply with Z for both half and one. So basically, we have shown you how to do this, okay, through the exercise 4. And what I want to highlight here is depending on which method you are adopting, you have different approximation for S. If you are adopting your forward method, your S can be substituted by Z minus 1 divided by T. If you are adopting your backward, your S can be represented or can be substituted by Z minus 1 divided by Z. If you are adopting the trapezoidal, your S can be substituted by 2 over T multiplied with Z minus 1 divided by Z power. So first of all, as I mentioned, there is no identical equivalent Z function to your S function. It depends which or what approximation you are adopting. How do you understand it? Understand it is simple. Because your S operator in your continuous time domain means differentiation. Then for different differentiation, you have different way to approximate it. Unus forward, unus backward, trapezoidal. And for any of the three, you have the approximation of differentiation by difference equation. Then for the difference equation, you can use the Z transform. Then each type of the approximation, you can find out a Z function. So basically, this Z function is to approximate your differentiation in your forward, in your backward, in your trapezoidal. So it depends which approximation you choose. Then later you have a different substitutions for your S function to get the equivalent Z function. Okay, so this is the detail how you can get it. Okay, if you are looking for the forward differentiation, your differentiation is your next step minus your current step divided by T. So if you look at the differentiation, it means you use this one to divide by the S transform, you get so what we mean is, if you have your differentiation of yt,
S
for the differentiation of yt, you put the Laplace transform, you will get your S multiplied with ys. If you do the transform of this one, you will get your so if you use S multiplied with ys, you divide by your ys, what you get your S. So for this one, you use your differentiation, you divide by your yz, what you get? You get your equivalent S in your Z domain. So this is your Z minus 1 divided by 1. Okay, similarly for the backwards. And the trapezoidal, just slightly more complicated.
我现在在抄，有没有抄到上面？
啊？
我抄错忘记了。
So this is how you derive the S operator for the trapezoidal. So after you get these three equivalents, then it's just depending on which method you are adopting, then you are able to get the approximated or discrete equivalent transfer function. So for example, if we have a low pass filter, and for the low pass filter, the S function is A divided by S plus A. I hope everybody okay with this one, right? Are you able to come out a low pass filter transfer function? No? If no, then you cannot solve the exam question last year. Because last year they assumed everybody learned well in the dynamics control, so they ask you to find out discrete equivalent for low pass filter. They are not giving you this one. But if let me see, if they told you it's a low pass filter, then you should be able to write a low pass filter is. This one is something the same as the example. Okay, if you want later, you can use it. So we have a low pass filter, which is
很惊喜，看他有东西。
A divided by S plus A. So what does this one mean? What does this low pass filter mean? A is what?
要是我错了，我就不知道。
What is A?
你说
What does low pass filter mean? If you look at the frequency domain, the low pass filter will only pass the low frequency, right? And will bypass the high frequency. So what is your cutoff frequency? What is your cutoff frequency? Don't tell me you don't know. Then it will be very amazing how you pass the definition. So what does this A mean? If your frequency J omega, if omega equal to A, what will be your function? If you look at the frequency domain, use the J omega to represent your S. If your omega is equal to A, what is the gain? Is it your minus 3 dB? Is it something called your cutoff frequency? No. This one, what I understand is there should be no, because last year in the exam they give the question to see you want to design a low pass filter and the cutoff frequency is 10 million per second. Then you should be able to write a low pass filter frequency which is 10 divided by S plus 10. Okay, very simple. When your omega is A, J or JA plus A, what is the magnitude? Root square of A, right? Root square 2 of A, right? A divided by A cancel each other, so it's 1 over root square 2, right? Then you take the log, it should be minus your 3 dB, right? And this one is something called your cutoff frequency, right? Okay, anyway, assume you know that. So if let me say you have no pass filter, you design in your S functions, and this is your continuous domain.
可以讲明年准备的话，老师都会测。
So what does this one mean? This one you can also rewrite as a differential equation because if your s function
omega.
is a divided by s plus a, and this one is your transfer function, your output divided by your input.
不懂。
So what we can see, a es is equal to s plus a us. So if you do the time domain, a times et, and this one is s multiplied with us will be your differentiation. And if we assume your initial condition is 0, okay, remember one of the things we have assumption in the dynamics control and also in this course because we are only dealing with the partial control, which means all your initial condition is 0. Okay, when your time before your initial time is 0. Okay. So if this one get your integration, what you want? You want to have a function about your ut. Then ut is what? Ut is your a et minus your aut. This is differentiation, so what do you need to do? You need to do the integration, right?
A 什么
You need to do your integration.
？minus 什么 A 什么 A 1
AUT，它直接 integrate 那个 U 到 T，直接 integrate。
So for this integration,
看呢？它是这个意思吗？
what you can do, once you have the differentiation or once you have integration, you can try to get an equivalent difference equation. So if you want to know what is your UAT in your digital domain, you look for the difference. So you look at the previous step, which is UAT minus E.
整个模型，它是一直
Then you get to do that integration, which is from your a minus 1
所以
e to your 3.
头发哦，
A is a constant, and put the a outside.
剃光头发，你给我盖住，谁看得到你问你？哇，说这个。
为什么没读？
So what you mean now?
头晕进去的。
This one is my difference equation. This is a difference, right? The difference between my current output and my previous output. What I need? I need integration of ET, I need integration of UT. So depends which method you are adopting. You may have different equivalent discrete equation for that part, right? So this one basically is over your area. Okay, from your previous moment, a minus 1t, to your current moment, at. So if you are adopting your Euler's forward, so what you get? If you are copying the Euler's forward, then your area will become